Good morning. This is a demonstration video to demonstrate the work which I have done for the J component of course image processing for the summer semester of 2021 and 2022. So the title of my project is Command Based Image Manipulation using CUDA. Let's go to the abstract. So parallel processing has seen its increasing importance in today's day and age, and increased computing benefits have provided by parallel computation have greatly benefited existing application and have enabled existence of newer systems as well. Now the thing is, we are trying to create a command based image manipulation using CUDA. So starting with CUDA, what is exactly CUDA? So CUDA is a parallel computing platform and programming model created by NVIDIA. CUDA works with the CUDA cores available in NVIDIA GPUs to parallelize large tasks to improve execution times. As we all know, graphics processing units or GPUs are specialized processing units that are designed to be very efficient in manipulating computer graphics and images. And this is why precisely I have chosen to do this project, because of the massively parallel opportunities we get in conversion and operation image operations we see in day-to-day life, like converting a RGB to a black and white or applying a convolution filter and many other stuff. And one of the benefits is that CUDA works with CUDA cores which are available in NVIDIA GPU, which parallelize large tasks and improve the execution times. Now, multi-threading has uses in many domains, and any task can be parallelized. Any task that can be parallelized can benefit from multi-threading, and most of those tasks can be related to images, since let's say we start with video rendering to image enhancement, and all other stuff can be uh, parallelized via multi-threading and multiprocessing. So we have tried to achieve those operations using CUDA. So like this is our example of CUDA. Like compared to simple ARM or x86 processors, our normal CUDA has lot of SIMDs, which we call single instruction multiple data processors, which can actually help us process all the data parallelly. So what is our proposed methodology to actually work with this? So transforming images by combining or transforming pixels in the original image and mapping them at different indices in the result images. So mostly we are going to do two to three types of transformation. Number one is pixel to pixel transformation, where we take each pixel and transform it in the output image. Some examples can be like RGB to black and white. Then you have gamma correction, contrast adjustment. All of this can come under pixel to pixel transformations, where we assign each thread to each pixel, and then that thread goes on to uh, transform that pixel individually to the output pixel. So if you imagine all the other parallel threads working at the same time, we can get our result quite quickly. The next type of operation which we are trying to do is image warping. In this transformation, each pixel in the output image takes its value directly from a different position in the input image. So we are mapping each pixel in input image to another pixel in output image through a variety of trigonometric functions. So as a result, the dimension of the image change, or the image needs to be cropped in to maintain the same dimensions. In any case, the memory for the image needs to be reallocated. In a project, we include like image rotation and radial distortion. Finally, we have general transformation, you can think of convolution matrices. So we are trying to incorporate a sharpening filter in our command line utility as well, which will sharpen by using a 3x3 convolution filter. So this is the proposed methodology. So basically how CUDA works is, we will have the array of pixels when we import that image in our main memory, and we're gonna allocate memory on our GPU, because GPU is a different device. In CUDA terminology, the host is the main CPU who schedules the task. So our, in this case, the CPU is our main processor and the computer RAM which we have, and device is the GPU, and device has its own memory as well. So to allocate, first we have to allocate the GPU's own memory, and then we have to copy the image inside the GPU memory, and then we have to call the kernel to start processing. Once the processing is done, we have to copy back the result from the GPU memory to our own memory, and then we can save that stuff. This is what's happening in the PPT, like we are copying, processing the data, copying the result. First instruct the processing, then execute, and then finally copy the result back. So this is the memory for the GPU. This is a better, in this case, methodology. So we'll get the array of pixels of images using OpenCV, convert them to CUDA processable format UCAR4, since CUDA needs a specific type of data UCAR4 which has 4 dimensions in each data type, X, Y, Z and W. This can be incorporated for X, RGB and A format. And finally feed the data into the function which will allocate and copy the memory on device GPUs, run the kernel to process the image, and copy back the image back to the host memory, which is the computer RAM in this case. As you can see on the left hand side, there's an image. We copy the input to GPU device, and then we call the kernel from the host device to actually operate on the image inside the GPU. It executes the kernels for all pixel location, and then we copy back the output from the device memory to our host memory. The formulas which need to be used. So as I had said, this is this basic formula for black and white. So like we are going to multiply 0 to 9, red pixel with 0.299, green pixel with 0.587, and blue pixel with 0.114. Gamma correction is like a transformation which is very important due to the fact that camera sensors record light intensities and display screen display intensities linearly. So this is mostly used in old CRT monitors. When twice as many photons hit the sensor records doubles the value. This is not the case in case of human eyes, which responds much better. So due to this imperfections, we need to actually change the gamma value when we're trying to, or I should say correct the gamma value when we're trying to output the image through older television screens like CRT, which can actually incorporate for the change in brightnesses and all the ratios of red, green and blue. So these are the formulas which we have used for like red, green and blue. Now we move forward. The rotational translational type operations which we used are this thing, rotation and radial distortion. So like rotation in this case involves rotating an image about an axis through the center of an image through an angle specified by the user. Obviously positive is counterclockwise and negative is clockwise. Implementation of this being a simple image will warping operations use the following formula to calculate the position of the input image and each position the output image. And radial distortion is a failure of a lens to be rectilinear due to which straight lines are bent as a general curve. So we can actually correct radial distortion and also incorporate more radial distortion, and these are the formulas which we use for this. Moving forward, finally we have a sharpening convolution as well. So here we will try to convolve our image with a specific mask. In this case we have taken this mask which is valid for um, uh, X and Y, horizontal and vertical. It can actually detect the horizontal and vertical edges, and then it will apply sharpening filter on that one. We can also use it for the diagonal version as well, which will have -1 on the nearing 8 neighbors, and the center pixel will be 9. It can be incorporated as well. And yeah, so this is what the sharpening filter is about. Now moving on to the demonstration of that. So this is a main code, main function. So this is just a command menu loop because it's a command based interface. So first let me execute this one, and then let me show you what this actually can do. Let's start this. So first we have to load the file path, in this case resources. I have a picture. Let's open this resources. Suppose we want to take this one, this image. Then we are going to, now we have to actually enter the specific commands which we want to do. Like say I want to say example, I want to sharpen the image first. Then I want to rotate the image by say 90 degrees, or let's say 45 degrees as well. Then I want to um, then I want to black and white the image, convert it to black and white. And finally, once all the commands are in queue, we can process the image. And once the processing is done, we can save the image to the destination which you want. Say that I want to name the image file as Lena Sharpen, then wrote 45, and then final black and white dot. So we can save it as JPEG as well. We can save it as PNG as well. Now we go back. This is the Lena Sharpen Road 45 black and white, the one which we have just changed. Comparing it to the old picture, this one, we sharpened the image, so you can see the sharpening as well. We rotated the image for 45 degrees, and we also have applied the black and white filter on this as well. And since the output will be smaller than this, we had to incorporate for the padding of the pixels as well. Now let's go to the code demonstration. So this is the main function. Now, as I had said before, that CUDA requires a specific data type to work with, and that is uchar4. Most of the data types which we will encounter in CUDA will always have a dimension with it. Like it might be a fourth dimension data, third dimension data, and here we have first I'm loading the file path, and this is the uchar4. I am already giving a pointer to that image and the height and the dimensions, and this is the image which function which I wrote to actually convert the data which I get into uchar4. So if we move on to image q.h, and here you have to search image loading. Yep, this one, load image RGBA. So basically it takes that image which we have given it, the file path. Now basic thing is reads via OpenCV, but after that it will check if the image is valid or not, or if the image is continuous or not. Finally, if it is, then we are converting that image into uchar4. We are first allocating the space for uchar4. The size will be the total dimensions of the image, rows into columns, width into height, and then we are going to map each of the RGBN pixels to their X, Y, Z, and W dimensions. As I had said, uchar4, 4 stands for that unsigned character. In this case, unsigned data type will have 4 dimensions. So in case we don't have the 4th dimension, it's a 3-channel image. We're gonna give the last channel as 255. If we do have, then we're gonna map it as well. And finally, since it's mapped into the memory space as well, we don't need to return anything. Coming back, this function, whenever we are going to trying to enter any kind of command, it will actually store that inside a q.push command. And finally, when we call the process, what it does, it processes it pops each of the command which we have given in the queue one by one, and it keeps on processing. Like if in the example we had actually called for sharpening, then rotating by 45 degrees, then again converting to black and white. So it will first sharpen, then convert to rotate it to 45 degrees, and then finally convert to black and white. Each of these are executed in the same sequence which we have given. Now the important portion is this one, image command, where the kernel is actually written. Here we must go back to the slide which I demonstrated. So CUDA works like this, that we have a function on the host device on the host, which is a CPU. What the function in the host does is Since host is a CPU and device is the GPU, and device memory is different from the host memory. So first of all, we need to actually allocate memory on the device itself. So here CUDA malloc can come in place. You can see just like how we use memory allocation malloc for memory allocation in host device, we can use CUDA malloc for memory allocation in the device memory. And then we have to copy the memory from host RAM to device RAM. That's where we use CUDA mem copy. As you can see, we are using this the size, and finally CUDA mem copy host to the device. This means that we are sending the image from our CPU RAM, computer RAM to GPU RAM. And finally, this is the kernel to convert to process the data which we have in this format. So this chevrons, inside these three chevrons which you can see, these are the launch parameters. So the concept of CUDA programming is that each of the threads which we have, we call them warps, and all those threads are organized in 32 in groups of 32, which we call as thread block. Now each thread block have their own shared memory, and all those thread blocks can be also thought of as a grid. And the thing is, um, we always the GPU will always try to group threads into blocks of 32. So it's very crucial that we select our thread blocks as thread number as a multiple of 32, and the thread blocks as a multiple of 32. Otherwise, if we don't, the GPU will itself anyways assign it as a multiple of 32, and then we will have a lot of unused thread memory. So it's better to define it by ourselves to be multiple of 32, so that we get the complete efficiency. We can achieve the complete 100% efficiency of all the threads. So this, as I had said before, CUDA always likes to represent its data in a dimension format, and for logical purposes, this dim3 is a construct which takes in 3 parameters, and instead in this case we have given only 2 parameters. So first parameter actually defines the number of the first parameter actually defines the number of thread blocks in a grid, and finally the second parameter defines the number of threads in a block. So as I said, we are taking 32 threads in a block, 32 threads. The last one we don't need anyways, because we're not gonna do it for Z. We have taken only 2 dimensions, x and y, which will be working as I and j, since we are going to traverse the we're going to traverse the square rectangular image array, pixel array. So coming back to the basic kernel, this is a pixel by pixel operation. First of all, we need to understand the ID of the thread which it is. So we can find it very easily by that we are going to multiply the block ID number multiplied with the block dimensions. It will be 32 obviously, and this is the offset, the next thread ID. Using this we can get the thread number in the complete grid. Same goes for y, because we are doing it for 2 dimensions. And finally we can get the actual ID, since the memory since the pixel arrays, they are allocated continuously in the GPU memory. So we need to find the actual ID by we'll be multiplying x with the width of the image plus y. And finally this is the formula which we all know for converting a RGB image to a black and white. As we have seen, this is where the usage of uchar4 shines. Since we have 3 different dimensions, we can actually work with the x dimension, y dimension, and z dimension, which we have assigned as red, green, and blue. If it was a 4 channel, we could have used the a dimension as well, which in this case is w. But anyways, we have got the black and white value, and we are assigning it to all the 3 pixels RGB, converting it to black and white. The next step of command which we discussed was a rotation and distortion. These are kind of trigonometric mapping commands. So we move back. This is our rotation command, rotate image in this case function. So same things as before. We have the dimensions, we have the output dimensions. We are pre-calculating the output dimension, because as we all know, the image, if rotated, there it might shrink a bit. because it has to still fit in that square location. That's why we are calculating the output size. And this is the image output. We are also recalculating and reallocating the output memory, and finally we are allocating the memory on the GPU. um, and then I'm copying the memory, copying the image into the device memory, finally calling our rotate kernel. So this is a rotate kernel, this one. So we are, as before, we have understood what x and y are. We're finding the ID. We got the RGB because all of the rotations must be done in the same order, so all the pixels should be mapped in the same order. So RGB, we are just doing this for each of these dimensions. Sorry, wait a second, this is gamma correction. This is the rotate one. Yeah, so this is the output image, and this is the input image. So we are using the trigonometric function to actually map each of the pixels. In this case, we don't have to do anything with respect to each dimension, because if we take each pixel as itself, we are considering all the three dimensions: red, green and blue. So just a simple mapping function with trigonometry. And same goes for your radial distortion as well. We have to calculate the output image before, and then finally we have to call the kernel and work with it. Finally, when we talk about the sharpening the convolution kernels, there's a bit of more code which we had to put in, because there's a concept of padding, because image will always try to shrink when we try to apply convolution. It depends on the size of convolution we try to include. Like smaller convolution will shrink the image lesser, larger convolution will shrink the image more. So here in this case, what we have used the concept of shared memory to actually um, communicate to all the other thread blocks that we are actually adding a same padding. We have used same padding in this case on the edges. So there is a if else block to actually incorporate for all the top, bottom, left and right edge. And at the end we are synchronizing threads, because now we are going to begin the actual operation of applying the mask. How did we actually apply the mask? So we have a 3x3 mask. uh, this is the kernel. We have also supplied the kernel, we have also supplied the mask with it, the mask 3x3. The mask is this one: 0 minus 1 0 minus 1 5 minus 1 0 minus 1 0. So we are considering each pixel to be the output pixel which we take, and each pixel is trying to convolute all the mask by considering its 8 diagonals. So that's why we have two loops which can incorporate in the 9 pixels where we are going to apply the mask. And from minus 1 0 minus 1 minus 1 0 minus 1, like that one. And even after that, we are facing a little bit of issues, because a lot of the pixel values were going out of the range from 0 to 255. So what we did in this case is we tried to clip the pixel values from 0 to 255 only. So if it's less than 0, we'll clip it to 20. If it's greater than 255, we'll clip it to 255 itself. And finally we are keeping the value to image out and then copying back the image. So this is all what I have to say. I tried to also incorporate skew image command, but it didn't work well, and due to time limit constraints, I had planned much more than this, but due to time constraint, I wasn't able to completely uh, complete all the kernels in this case. So yes, all of these are here. Let me show you this one as well. So this is some more examples of how everything is being done. So we have input image to black and white. We have input, we are rotating it by negative degrees. Then the gamma correction is here as well. This is radial distortion, positive radial distortion, negative radial distortion. And then the sharpening is there. And this is the command which we have. So yeah, I guess that's all I have to say. I hope you like my demonstration, and thank you for watching this video. Thanks.